Welcome to the third module in our series on professional development for high school teachers to integrate quantum concepts into their classes. At the top of Module 3 is a recap of everything we did in Module 2. We start with the recap of what these column vectors and row vectors look like in a spin 1/2 system so that you can keep track of the spin up state and the spin down state along the z-axis. And we're going to review how any beam of electrons you can model as a linear combination of those two states. So C plus and C minus are just constants. They're just numbers that you pick when you're modeling the beam. And they give you the probability of each spin measurement. So the probability of measuring spin up is the modulus of C plus squared. The probability of measuring spin down is the modulus of C minus squared. The actual act of measuring along the SZ axis can be modeled using this 2x2 matrix, which you then multiply onto the two states, plus or minus, spin up or spin down. And that really contains everything you need in the model in order to understand or predict what's going on in one of these Stern-Gerlach experiments. And so what we're doing in this module is extending this to the x direction and the y direction as well. We start out with the x direction. So instead of spin up and spin down, you could call this spin left and spin right. And what's going to happen here is that you're polarizing the beam along the x-axis or along the negative x-axis. And so we just call those plus and minus with a subscript x here to remind us that it's along the x-axis. Now remember, the spin up and spin down, the original plus and minus states, those are what we call a complete basis, meaning any other state can be described as a linear combination of those two states. And so what we have to do is figure out what these four coefficients are, A, B, C, and D. And this is going to walk you through that process of getting two of the values, and then we ask you to figure out what the other two values, C and D, are going to be. The code is very similar to what you saw in Module 2. We create the spin up state and the spin down state as just 1, 0 and 0, 1. Then we're going to put in our coefficients we have here. Again, you're responsible for figuring out what C and D are here. And then we'll create spin right and spin left. That's the plus x and minus x as our linear combination here. And then we can check on the properties that we need. We've got the probability of measuring it up, the probability of measuring it down. That's just given as the modulus squared here of each of those inner products. And it will print all that information that you need there. And the goal is just to check to make sure that those results come out to what we expect it to be, what it's supposed to be, given the experiments that we conducted at the beginning of Module 2. Next, we extend that model to the SY states. So you might call these spin forward and spin backward. That's the only direction that's left for us in 3D space. And again, we need to represent these in terms of our existing spin up and spin down state. So we need to figure out another set of A, B, C, and D. The problem here is that we've already used a set for spin left and spin right. You should have figured out that those were a combination of 1 over root 2 and negative 1 over root 2, just with the negatives distributed strategically. So how can we get these to be any different? Well, this is why we talked about complex numbers back in Module 1. This is where we're going to use complex numbers because that gives us an extra bit of mathematical space to move around in. And so it turns out you can make this work if you make A and C equal to 1 over square root of 2, just like you had in the SX states. And then here, to get B and D, we've got to tack on a square root of negative 1. We've got to take the imaginary number J and put that in the numerator in place of a regular 1. Notice it's still going to be plus and minus so that we'll end up with everybody having the appropriate inner products that we need, but we need those imaginary numbers for this to work out. So what we're going to do, again, set up spin up, spin down, and we just set up A, B, C, and D here. We use our 1 over root 2s, but this time around we're going to be adding in a J on B and a J on D. Remember, this is Python's way of denoting square root negative 1 is just with a 1J written just like that. So just like we did before, we're going to make spin forward and spin backward. Now here what we're going to do is ask you to check the probabilities, right? We know that if you have a spin forward beam, it should be a 50-50 probability of measuring spin up or spin down. So you should get an inner product, you should get a probability here of 50% and 50%. We're going to leave it to you to fill in the inner products here. You can use the code cell from the second step on S sub x in order to figure out what those inner products should be. Well, now that we've got the states in the x, y, and z directions, it's time to start talking about the measurements in the x, y, and z directions, right? Because spin is a vector. It has three components, x, y, and z. But spin now is an operator. It's now a matrix. So we need three matrices to represent spin. We need a matrix for the x direction, a matrix for the y direction, and a matrix for the z direction. And it turns out these combinations will work. Notice everybody's got to have an h bar over 2 because you're always going to measure h bar over 2 for the spin. In any direction you measure it, it's just a question of whether you measure in the positive direction or the negative direction. And so what we've got here is the combination of matrix elements that will give you the appropriate spin states when you take the eigenvalues and eigenvectors of this matrix. So for Sx, we need zeros on the diagonal and ones on the off diagonal. For Sy, it looks much the same. We've just got j's and a negative on there. And for Sc, we've got what we had last time, 1, 0, 0, negative 1. Again, we can create these matrices in Python so that Python can do the math for us. So we've got our h bar over 2's, and we've got our array set up with all those elements that we had before. We've even printed them out to make sure that that works out. So what we're going to ask you to do is try out some matrix multiplication. So take this code cell here, modify it to carry out each of these calculations. Now some of these you'll probably be able to intuit what it's supposed to be. So like Sx on plus in the x direction, you know that's going to be a plus h bar over 2, just like it was for Sz and the plus state. Is that what you get though? That's what we want you to check on, is whether your setup here gets all the appropriate answers for these multiplications. Last time we talked about modeling measurements with eigenvalues, that when you take a measurement of a spin, you're always going to get an eigenvalue of the spin operator, the spin matrix, in that direction. So for example, when you measure Sz, you're always going to get plus or minus h bar over 2, and you're going to find out that it was in this state or this state. Same thing with S sub x, you're going to get plus or minus h bar over 2 measured onto this state or this state. Same thing with Sy. So what we're doing here is having the computer tell us the eigenvalues and eigenvectors of these matrices, because getting eigenvalues and eigenvectors, you can do it by hand. It's kind of a long process. So this is exactly why we have the computer here. And we're taking this for S sub x. We'd like for you to do the same thing with Sy and Sz to make sure they all give us the appropriate eigenvectors and eigenvalues. Of course, when you're conducting an experiment involving spin, you're rarely going to measure the spin of a single electron. You're going to measure all the spins of a whole bunch of electrons flying past you, and you're going to get an average. Well, remember, we call average an expectation value in quantum mechanics. And the way you calculate an expectation value, if your electrons are coming to you in a state psi, then you just take the thing you want to measure, let's say Sz in this case, and you place it in between two copies of psi, one for the ket, one for the bra, the complex transpose. And so if you want S sub x, you replace that with S sub x. If you want S sub y, you replace S sub y. This is going to be the average for many, many measurements that you take with that beam of electrons. And so we've got a code cell here for you that creates all the spin states that you need. We've gone ahead and set up all 6 of the spin states and all 3 of the matrices, and we want you to set up psi. We want you to set up the beam with a certain percentage in the up direction and a certain percentage in the down direction, and we want you to use that to calculate the expectation values of S sub x, S sub y, and S sub z. Now you notice we've given expectation value in the x direction for you to start with, and then we're asking you to copy, paste, and modify that to get Sy and Sz's expectation values. And this will create a nice little visualization where you're able to compare what each of these expectation values is. The next set of questions asks you to take your code and use it to match the experiments we did way back in Module 1, when you were using the simulated Stern-Gerlach experiment, you were able to get all these interesting outcomes where you could separate spin up and spin down, take all the spin up, separate them into spin left and spin right, and then separate those again into spin up and spin down. I thought the spin downs got separated out farther below. We want you to use this code to create a simulation that matches those experiments using the matrix math. All right, now comes one of the coolest pieces of quantum mechanics, the uncertainty principle. You've probably heard this popularized in media. You might even remember it from a physics or chemistry class. But the basic idea of the uncertainty principle is that there are some measurements that you can't know concurrently. So these spin matrices, Sx, Sy, and Sc, they have this interesting property where you can't know two of them at once. So like if you measure S sub x, you're interfering with the S sub y measurements and vice versa. The way you can mathematically observe this is with the standard deviation. Remember, standard deviation is a complement to the average because the average tells you about where the middle of all your measurements are going to be, and then the standard deviation tells you how far away those measurements typically are. So here I've got a recap of the standard deviation calculation. It's the expectation value of the square of the matrix minus the square of the expectation value of the matrix. I always have to look that up. I don't remember that from the wording. And just remember that when we have it doubled up here, we just mean that you apply the matrix twice. So for example, you can do this in the code down here. We've got for you the matrices. We want you to set up the psi, and we've got the expectation value of the first piece, the SZ times SZ. So you notice we've got just SZ multiplied by SC here, and then we place that into our calculation here with the size. We're asking you to repeat that process for sigma y and sigma x, and we're also asking you to fill in the second expectation value where you take the square of the expectation value here. You actually have that already calculated in a previous cell, so you can go back up for that. And then we're just asking you to take a look at what happens with each of these sigmas, x, y, and z. Particularly, can you ever get them all to be 0 at once? Can you ever get an exact measurement in all three dimensions? All right, last piece we'll take a look at. There is one more spin matrix. Since spin is a vector, that means it has a magnitude. Well, how do you get a magnitude? Well, you use the 3D Pythagorean theorem. You take x squared plus y squared plus z squared. That becomes your spin magnitude squared. So this is another operator. This is another thing that you can measure. And what we want you to do here is take this s sub x, s sub y, and s sub z and use those to calculate the s squared matrix. Use those to print the s squared matrix and s squared times psi. And I want you to tell me what you notice about what comes out, because the s squared matrix is a very special matrix. And if you've had any experience with matrices, I think you'll recognize it right away.